Hello all. In this video we are going to discuss an important and interesting astronomical phenomenon during the observation of distant star from Earth with the telescope. Our Earth goes around the Sun with an incredible speed of 32 km per second. Our Earth is moving in space. So when we observe a star with the help of a telescope, we have to change the direction of telescope as Earth go from one point to the other on its orbit. The star cannot look at the same position at the same time every night because the position of the Earth changes as it moves in its orbit around the Sun. So when you look at a star through the telescope every night at a certain specific time, the same star will not be appearing at the same position in the sky. The position of the star will appear to shift because the Earth no longer exists at the same position in space as it is moving around the Sun. So we always have to change the direction of telescope in order to see a particular star in the night sky at the same time every night. Earth also spin around us. So all the stars in the night sky appear to go from one side to the other side. So we always have to change the direction of our telescope in order to track a particular star in the night sky. But every night, if you want to look at a particular star at a specific time, in that case also we have to change the direction of telescope every night because the Earth is moving in its orbit. So the position of the Earth relative to distant star is changing, and because of this we have to change the direction of the telescope so that it will point exactly at the star being observed. Stars other than our own sun are much further away from us. Consider one such star. At a certain moment, if we are here, then light from this star will arrive at us in this direction, and our telescope must be pointing along this direction. At a later time, when Earth is at this position on its orbit, the light from the same star will arrive in this direction, and we must change the orientation of our telescope. Now our telescope must point in this direction. So we have to change the direction of our telescope. It was this direction when the Earth was at this position on its orbit, and the direction of telescope needs to be along this arrow when the Earth is at this position. So we have to change the direction of telescope in order to see the same star, and this is because of the orbital motion of Earth. When Earth is at position 1 as shown, this white line represents the direction of light coming from the star. When Earth moves to the new position, say position 2, line 2 represents the direction along which the light travels from the star. So, at position 1, our telescope must be pointing in a direction along the line 1, and at position 2, our telescope must change the direction and now point along the line 2. So, we have to change the direction of telescope means we have to rotate the telescope through certain angle. The angle through which we have to rotate is phi. That we have to change the orientation of the telescope in order to see the same star because of orbital motion of the Earth. This is known as parallax, and the angle through which we have to tilt the telescope is called parallax angle. Here we have drawn line 1 again parallel to its old position here, and the angle between line 1 and line 2, which represent two directions of the telescope at two different earth position to see the star. The angle between them is called parallax angle. However, the stars are so far away from us that the angle subtended by the stars with the orbit of the earth is very small. That is, suppose the star is present here and it is very far away from earth. So earth is so far away from the stars that the orbit of the earth looks very tiny from that star. And therefore, as earth move along its orbit, the change in the angle between the lines from the star is very small. That is, angle subtended by earth's orbit at this star is very small. So as earth orbit, the angle through which we have to tilt the telescope is negligibly small, and therefore the parallax effect is negligible for almost all the stars because they are very far away from us, and the angle subtended by earth's orbit at those stars is very small. So practically no parallax is detected. However, we still have to tilt the telescope through an appreciable angle because there is another effect that exists, and that effect is called stellar aberration. Suppose that our earth is stationary in the universe and there is a star directly over it. And suppose that we are standing on the upper pole of earth and we are observing that star. The starlight falls directly downward. So when we are at the upper pole of the earth, we have to set our telescope vertically upright so that it will receive the light from the star and the star can be seen through the telescope. So here is the telescope. The figure is not to the scale. So telescope is exactly upright and the light enters the telescope through an objective and travels all the way down along its axis and reaches the eyepiece of the telescope where the star image will be formed and the star will be visible from the telescope. If the earth is stationary relative to the star and if the star is directly overhead as shown, the telescope must be mounted upright so that the starlight entering the telescope through the objective travels all the way along its axis and reaches the eyepiece at the bottom and the star becomes visible through the telescope. Our earth is not stationary in the universe. It's a well-known fact. It's moving. So considering earth moving, will it affect the observation of star directly overhead with the telescope? Can we continue to set our telescope vertically upright and be able to see the star? Or will we have to change the direction of telescope in order to see the star just because the earth is moving? Let's see what happened. We only show the telescope and not the earth. So we see that the telescope is moving in a horizontal direction towards right. It is actually the earth that is moving in the space and the telescope is stationary on earth. And these blue lights, these blue dots which are falling downward, they represent shower of light from a certain star that is being observed. Now at every position of the telescope as earth moves, the light from a particular star being observed will appear to fall directly downward. Means because the stars are very far away from the earth, the direction in which the light from that star arrive at the earth does not change appreciably. So as the earth moves, the change in the direction of starlight received by the earth is almost negligible because the earth orbit looks so small from that star. That is, The angle subtended at the star by Earth's orbit is very small, and therefore the starlight appear to arrive at the Earth in the same direction. That is why as the telescope moves, we see that all the starlights are falling in the same direction at every position the telescope taking. We can clearly see that the starlight is not reaching the eyepiece of the telescope because of the motion of telescope. The starlight, on entering the objective of the telescope, it continues to travel vertically downward, but because the telescope is shifting horizontally, the starlight once entering the telescope cannot reach the bottom of the telescope because the telescope have already escaped because of its horizontal motion. So starlight entering the telescope will not be able to reach the eyepiece of the telescope. It will end up hitting the side wall of the telescope, and no star image will be formed and no star will be seen if we continue to mount our telescope in vertically upright position. So in order for the light entering the telescope to reach the eyepiece of the telescope, we must change the orientation of the telescope appropriately. As the earth moves in space relative to the stars, the telescope will be moving relative to the shower of light from particular star being observed. Since the stars are very far away from the earth and the speed of light is very large as compared to that of the earth, there is apparently no change in the direction of light as the earth moves in space over a considerable duration of time. Let's see whether the starlight entering the telescope from its objective can make it to the eyepiece of the telescope when the telescope is moving. We note here that the motion of the telescope is perpendicular to the direction of starlight. So our telescope is moving in a horizontal direction perpendicular to the direction of light, and here we can see that the light enters through the objective and it ends up hitting the side wall of the telescope, and it does not reach the eyepiece of the telescope. No star image is formed and no star will be seen if we continue to set our telescope vertically upright. Let's draw a vertical line, and our telescope is in a vertical position, and we have already seen that with vertical position of the telescope the starlight never reach the eyepiece, no star is seen. So we will have to change the direction of telescope. Let's tilt the telescope clockwise. Now the angle through which the telescope must be turned depends upon the speed of the telescope, that is the speed of the earth, and the velocity of light. Let's now check whether the starlight on entering the telescope through objective can make it to the eyepiece of the telescope and star image can be formed. Starlight entering the telescope can now travel along the axis of the telescope and finally hit the eyepiece of the telescope where star image can be formed and star can be seen. The star that is being observed is directly above the earth. It is directly above our head, but we have to tilt the telescope. In spite of being directly overhead, we cannot set our telescope vertically upright to see the star, but we have to tilt the telescope. This is because of Earth's motion through space. This effect is called stellar aberration, that tilt we have to tilt the telescope relative to the direction of light. So we can no longer set our telescope along the direction of light so that light will enter and star image will form, but we have to actually tilt the telescope relative to the direction of light so that on entering the telescope the light could travel along the axis of the telescope and reach the eyepiece and star can be seen. Let's see it again. Light enters, travels along the axis, and finally reaches the eyepiece. The angle through which the telescope must be tilted relative to the direction of light, this is the direction of light, it's called angle of aberration. Now look at the triangle ABC. We have angle A 90 degree and tan theta is AC divided by AB. Now AC is the displacement of Earth or of the telescope and AB is the path traveled by light, and they have taken the telescope moved for the time t from the moment when the light hit the telescope at the objective up to the moment it hit the eyepiece of the telescope. So light took the time t to travel from objective to the eyepiece of the telescope. In that time light traveled the distance of AB and the telescope travel, that is the earth travel the distance of AC. So distance AC that earth traveled divided by the time taken is simply the earth's velocity, and the distance AB that light traveled divided by the time is the speed of light. And we have an expression for angle of aberration, tan theta equal to V by C. That is, the angle of aberration is theta equal to tan inverse of V by C. We considered a particularly simple case in which the direction of earth motion was perpendicular to the direction of light. That is, the star that was being observed was directly overhead. Let us now consider a more general situation where the star may not be directly overhead. In other words, the direction of earth motion and the direction of starlight may not be at 90 degree. Let's consider this situation. The direction of light rays will be parallel everywhere as the earth moves, because the stars are very far away from us and the change in the direction of starlight is almost negligible. So effectively we can assume that the light falls in a parallel direction everywhere as the earth moves. We are now treating the case where the direction of earth motion is not at 90 degree to the direction of light ray. To treat this situation, we consider a specific coordinate system, and let's call it the reference frame 1. These pink and white crossing lines forms a coordinate system or a reference frame, and our telescope is present here at a certain moment and it's moving in a direction shown by red line. We can see that the direction of light rays and the direction of the telescope, the angle between them is other than 90 degree. The direction of the light is the vertical direction where we see the blue dots falling. Blue dots represent light rays, and the red line represent the motion of telescope, that is the motion of earth, and the angle between light rays and earth motion is alpha, which is other than 90 degree. In this situation, some more modifications are required in order to see the star through the telescope. In this reference frame formed by pink and white crossing lines, the motion of the telescope makes an angle other than 90 degree with the direction of light rays. But it is possible to devise a reference frame in which the telescope would be moving horizontally, making an angle of 90 degree with the direction of light rays, and the situation will be just like the one we have treated, and our derivation will become simple. So now consider another reference frame. The reference frame formed by yellow and red crossing lines. This yellow and red crossing lines which form the reference frame 2, it is set in motion relative to the old reference frame. It moves in a vertical direction relative to the old reference frame. And our telescope is present at a point A1 in the old reference frame, and the point A2 represent the position of the telescope in the new reference frame formed by red and yellow crossing lines. Our new reference frame is moving vertically upward relative to the old reference frame, and in this new reference frame our telescope will appear to move in only horizontal direction. So here we can see the moving telescope. Our telescope move from A1 to B1 in old reference frame, and in a new reference frame it moved from A2 to B2, and the path from A2 to B2 is simply the horizontal path, as we can see. So in old reference frame the angle between the light rays and the displacement of telescope is other than 90 degree, but in new reference frame the telescope travel horizontally from A2 to B2, and the angle between the telescope motion and light rays is 90 degree. So now we can treat the adjustment of the telescope in the new reference frame, and the treatment will be similar to the one that we have just done. Let's view the picture in slow motion. The telescope moving from A1, A2, the points A1 and A2, they coincided at the beginning. The telescope moved from A1 to B1 in the old reference frame, while it moved from point A2 to point B2 in the old reference frame in a horizontal direction. The path of telescope in the old frame is represented by this white line, and the path of the telescope in the new reference frame is represented by this green line extending from A2 to B2. So here we see that the telescope is traveling in a horizontal direction from A2 to B2 in the new reference frame, and this direction is at 90 degree to the direction of light rays falling downward. Let's see it more clearly. Red yellow cross lines representing new reference frame, white pink cross lines representing old reference frame. Time t1 represent the time at which the light hit the objective of the telescope, and time t2 is the time at which the light is expected to reach the eyepiece of the telescope. Here light hits at time t1 and it is expected to reach the eyepiece of the telescope at time t2, but because the telescope is moving, the light is not able to reach the eyepiece of the telescope with the telescope is in the upright position. So when light hits the objective at time t1 again, if telescope were stationary here, it would have reached the eyepiece of the telescope here and the star image would have been formed. But the telescope continues to travel further and light continues to travel downward, and the light traveling downward misses the eyepiece of the telescope because telescope has moved. So this is the position when the light hit the objective of the telescope, and this is the position of the telescope when light was expected to reach the eyepiece of the telescope if the telescope had been stationary just at this point. So what should we do? By the time the telescope comes at this position, the eyepiece of the telescope must be at this position so that the light reaches the eyepiece of the telescope. So we will have to tilt the telescope in a clockwise direction like this. Now with this tilted position, as the telescope travel in this direction, the light will hit the objective, enter the telescope, and as the telescope moves forward and the light moves downward, the light would travel along the axis of the telescope, and finally when the eyepiece of the telescope reaches here, it will reach the eyepiece and star image will be formed. Let's see it. Now the telescope is tilted relative to the direction of light at an angle alpha. Sorry, not an angle alpha. It is the angle alpha is the angle of the direction of motion of telescope with the direction of light. So angle alpha is not the angle that the telescope make with the vertical. Angle alpha is the angle between the direction of motion of telescope and the direction of light, which falls downward. So actually alpha is the angle between Earth's motion and the ray of starlight. Let's see it again. The telescope moving at an angle alpha with the direction of light. Now the starlight entering the telescope. Now travel along the axis of the telescope and finally reach the eyepiece of the telescope. So with this tilted position of the telescope, the star light reaches the eyepiece and the star image is formed and star can be seen. So with the vertical position it is not possible to view the star, but with this tilted position it is possible to view the star. And we have to tilt the telescope not because the starlight is being received in starlight is emitted in that direction, but because of the earth motion, the direction in which the starlight is received is different from the direction in which the starlight is actually emitted. So it is the motion of earth that makes the difference and that causes the phenomena of stellar aberration to occur. Let's check it again. Here light entered at the time t1 and at the time t2 it reached the eyepiece of the telescope. In the time interval from the moment t1 to t2, the telescope traveled the distance from A to D. It traveled the distance from A to D in this time interval from t1 to t2, that is the time interval t2 minus t1. The telescope traveled or undergone the displacement from A to D, that is AD bar. And AE represent the vertical component of displacement and ED the horizontal component of displacement. The angle between the telescope and the direction of light is called angle of aberration, which is theta. In triangle EBD, the angle E is 90 degree. It's not A. The angle E is 90 degree. And tan theta is ED upon BE. And we can write BE as BA plus AE. Now, in time T2 minus T1, the light traveled from A to B. The telescope moved vertically from A to E and horizontally from E to D in time T2 minus T1. We divide numerator and denominator by T2 minus T1. We get this and then this. In the next step, this ED as can be seen is AD sin alpha, which we have written here, AD sin alpha, and this ED is equal to AD cos alpha, sorry, EA is equal to AD cos alpha in the triangle AED. In the triangle AED, we have ED equal to AD sin alpha and EA equal to AD cos alpha. So we substitute for ED and AE. We substitute for ED as AD sin alpha and for AE as AD cos alpha. ED equal AD sin alpha and AE equal AD cos alpha. Now AD is the displacement of telescope, that is the displacement of earth in time t2 minus t1. So AD divided by t2 minus t1 is simply the earth's velocity, which we denote by v, and therefore we write v for AD divided by t2 minus t1. This is AD divided by t2 minus t1 and AD divided by t2 minus t1. We replace it by v and we get tan theta equal to v sin alpha upon c plus v cos alpha. That is, we finally get theta equal to tan inverse of v sin alpha upon c plus v cos alpha, which gives us the angle of aberration when the angle between telescope motion or earth motion and the direction of starlight is other than 90 degree. This is the general derivation of the angle of aberration in a general situation. This derivation can be obtained by simple geometrical construction, but those geometrical construction does not give us the intuitive idea about why such geometrical constructions are made. We have tried to derive this aberration effect in terms of the more intuitive ideas about the motion of telescope and the direction of starlight and so on. So we have presented the situation in our own ideas, in our own intuitive way, which make it simpler to understand the phenomenon. Thank you.